Stories of our climate future, the use of storytelling and scientific investigation in climate change adaptation. The sound of story is the dominant sound of our lives. This quote, extracted from novelist and storywriter Reynolds Price, suggests the power of story to humans. Price maintains that storytelling is second only to food as an essential need. Therefore, we should expect story to be an important part in the practice of science, and especially in the interface between science and society. In science communications, this has been known for a long time. Many of us have been searching for the effective story for many years. This story, is about adapting to a warming climate and the formal use of story in the practice of participatory scenario planning. Scenario planning is a technique to manage complexity, uncertainty, and the usability of science-based knowledge to anticipate the consequences of warming, increase resilience, and to adapt. As the subject is much too large for the amount of time that we have, I will focus on the way to start to tell particular stories of a climate future. Scenario planning is a practice, a technique used to explore a set of plausible and coherent futures along particular paths. Plausible, in this case, we mean that it is consistent in principle with the laws of physics that govern our climate. This means that different parameters, for example, temperature and water, behave in ways that are coherent and consistent with physical principles. In general, however, plausibility will vary depending on the audience, their knowledge, and their beliefs. The stories have to represent the complexities that are the nature of our weather and climate. They have to span many paths to embrace uncertainty. They have to be developed in concert with scientists, practitioners, and all of those who are vested in the outcomes of specific challenges to planning, design, and management. If we look at the past couple of decades, there is a natural story that emerges. This audience is familiar with global climate models that motivate us to intervene in the use of fossil fuels in the management of their waste products. These models have been said to provide predictions or projections of our future. The natural story is that these models provide usable numbers that can tell us with confidence how to design, engineer, and manage our future. The mere fact that we have these piles of numbers convey a sense of high accuracy that is enticing but not justified. When we use this natural story, we find that the data are difficult, perhaps maddening to use. We find that the knowledge provided by these models is challenging to extract, uneven, uncertain. It requires expert interpretation. Despite these challenges, we have a responsibility to address the reality of a warming climate. We need to have techniques that support defensible use of model guidance. I use the word guidance. If we look into the world of professional weather forecasters, models and model predictions do not provide the forecast. They provide guidance that is used in concert with observations and theory. The forecast and its uncertainties follow from expert interpretation of all these sources of information and knowledge. Some of my best stories have come from prompts. Here are 3 prompts. First, assume that the models that we are using are not designed for adaptation applications. We are therefore trying to fit the simulations to applications for which they were not designed. Second, the simulations from prognostic models provide guidance, not predictions, not forecasts. They are at best telling us possibility and probability. They are not and never will be deterministic. Third, our stories need to embrace uncertainty, to be anchored in reality, and to be plausible to those using them. If I think about how I would build scenarios for climate planning, development of stories is central. The stories have to be meaningful to planners, designers, and managers. A good way to find meaning is to build them from known weather vulnerabilities. The stories will use model simulations to provide quantitative information to assure that parameters used to measure climate are physically coherent and plausible. The scenarios need to be punctuated with disruptions, fire, flood, tree fall, infrastructure failure. And a good scenario will frame the techniques for obtaining model simulations with defensible information suitable for design and engineering. I will only address how to start the stories that inform the development of scenarios. Once upon a time. All relevant, plausible stories are framed by physical principles. There is one premise that stands out from all others. The planet is warming, it is accumulating heat. The warming is not uniform, but varies in space and time, and on average it is hard to find a place on Earth that is not warmer from one decade to the next. The warming is directional, going up, and it will continue for decades. Here, I start the path. We know best the planet is warming, and it's productive to think about the responses to that warming. Next, and perhaps most important, how does precipitation respond to warming? There could be more precipitation or less. It depends on the availability of moisture, which comes from oceans, lakes, and the land. When moisture is available, there should be more precipitation. When it is not, there should be less. Since most places experience wet and dry periods, perhaps flood and drought, each outcome is expected. Variability should increase. Are the consequences we expect immediate? For more intense storms, more extreme precipitation. Are storms changing? More extreme precipitation is observed. It follows directly from warming and the availability of water. It is a robust signal of a warming planet. But is there more precipitation or less? Does it get wetter or drier? That is, the cumulative effect, the stuff of floods and fires, of high lake levels. The answer to whether it will be wetter or drier might be different in 20 years and 100 years. This depends strongly on if we intervene to limit the warming. This process of path building goes farther and farther, building complexity. More or less precipitation, above or below freezing, more intense, wetter or drier. Is it cold enough to freeze the surface of the lake? We need to add storms and events. We can come up with some rules of a good story. First, there is no one outcome, no one thing climate change will do. What is expected in 10 years, 30 years, 60 years, and 100 years might be qualitatively different. For example, wetter, then followed by drier. Paths are conditional with the conditions based on physical principles. Is water available? Is it above or below freezing? Climate scenarios depend on surface conditions. Climate scenarios need to consider the immediate instantaneous effects of storms and the cumulative effects of, especially, water. Disruptions often come from calamitous events, and recovery is in a different and changing climate. It is time for this story to end. In our work, we have found that, for now, many practitioners we work with are satisfied with the story ending here. But for some, we have not addressed that vexing problem of getting defensible, quantitative information for design and engineering. That, however, is a different story, one that is only beginning to be written. For now, here's what I want to convey. The challenges of adaptation place challenges on modeling capacity that are outside of the fit of purpose for most of our climate models. Scenario planning is a technique that supports planning in the presence of uncertainty. It focuses on plausible futures that assist, for example, contingency planning. It requires following the rules of storytelling. If done well, it should support the design of simulation approaches that are more suitable for adaptation. Thank you.